Thanks for coming. Appreciate it. All right, so like Todd said, I'm Rob Jacob. I've been at Tufts now a little more than 20 years, and I'm in the computer science department, but my field is human-computer interaction, so I sit sort of in the, they let me in, but I'm on the sort of edge of computer science, but we're all friends. So I've been working on, so let me start with this description of, turn this thing on, sorry. There we go. Yes. So I've been interested in various forms of new ways for humans and computers to communicate for a long enough period that new is a moving target. So I worked on virtual reality, eye tracking, as Todd said, tangible interfaces, various other forms of communication. And a high-level view, I think, is this one from Tufts, that's the visualization guy, who talks about two powerful information processors, if you stretch the idea a bit, connected to each other by a narrow bandwidth channel. So the limitation seems to be not the power of the computer or the human, but the width of the channel. We're just, what's holding us back often is the inability to get enough information across that channel. Lately, I would say, or for a long time, we've had better communication in this direction than in this direction. Computers can shower us with video and audio and surround pictures and things like that. But the input is still, sort of the keyboard and the mouse and stuff like that. It wasn't always the case. There was a time, this is for the old folks in the room, there was a time when input and output in an interactive computer system were the same speed. At early computers, interactive systems used a teletype. Anyone remember a teletype? There's probably somebody. All right, yes. I typed my thesis on a teletype. Anyway, used a teletype, and it had a typewriter keyboard, and it had a little printer. It would print out the computer's responses. And it worked 10 characters a second in both directions. So the speeds were not always so imbalanced, but now they are. And for extra credit, anyone know who those two people are in the picture? You got it, yes, good job. Yes, it's Ken Thompson and Dennis Ritchie, the people who wrote Unix. And they wrote it on, surely somebody knows what kind of computer that was. Yeah, of course, PDP-11, yes. I don't know which model, but PDP-11. That's what Unix was originally written on, a PDP-11. For younger folks, Unix is what Linux is a copy of. If that helps you figure out what you're into. Anyway, that's just a side issue. So there's been a general interest in ways to collect information from people in real time without them having to do very much explicitly. These are not synonyms. These are kind of like overlapping Venn diagram. These are various terms that include some collection of this kind of passive sensing interfaces that try to collect information that you just naturally emit and then use it for something. So with these kinds of interfaces, the user doesn't have to give explicit commands. These are used in addition to explicit commands. So you're there typing away, and then the computer can get extra information from your heart rate or your eye movement or something like that. So we're adding implicit commands to the existing explicit commands. And there are various things we can use. Today we'll talk about brain interfaces, of course, but other physiological sensors work this way. You get things like heart rate or skin resistance or things, physiological measurements like that, and other kinds of things you can just obtain. In each case, these inputs are not intentional. You did not purposely normally move your eyes somewhere in order to trigger the computer. You certainly didn't push your blood pressure up in order to trigger a computer command. So you didn't really mean very much by it. You didn't intend it. So you have to be very careful to use those kinds of inputs very gently. It would, excuse me, it would be really annoying. I used to work on eye movement interfaces. If you had an eye movement interface where when you look at something, immediately a new window opens, something else shuts down, this would drive you nuts. When I was working on it, we called it Midas touch. Anyone remember King Midas? All right, usually somebody does. King Midas was a greedy king, and he wanted gold so badly that he was given the power that anything he touched would turn to gold. And at first, eye tracking is like that. You look at something and bang, something happens. You look over there, something happens. It's really cool. And after a couple of minutes, just like King Midas, you're like, I just want to look. Leave me alone. I mean, King Midas obviously couldn't touch his friends, his food, or anything. Yeah. So you get this Midas touch phenomenon. And the only solution is a very careful, gentle interface design. Don't read too much into these very lightweight implicit interfaces. The temptation, as soon as you get an eye tracker, is plug it in place of the mouse and off you go. It's terrible. So you have to be more careful in the design. So what I've been doing is brain-computer interfaces in this general genre. So let's see. Get this. So we are a very small corner of the brain-computer interface world. Most people who work on brain-computer interfaces are doing this for severely paralyzed users. These are people who not only can't move their arms and legs, they can't even move their eyes. And in many cases, the tragedy is they have a perfectly fully functioning brain, and they just have no way to get out. It's sometimes called locked-in syndrome. It's absolutely tragic, and brain-computer interfaces have made fabulous advances for those people. But there's very few of them. I mean, this is not. It's a life-changing difference for a very small number of people. So we're doing the opposite, just because everybody else is doing that kind of BCI. We're doing the opposite in my group. We're trying to say, can we bring some benefits from brain-computer interfaces to a wide population? Now, we're not going to bring life-changing benefits, but what could we do for a much larger population? So in the BCI world, we live in a very small corner. To make our corner still smaller, most people who do BCI use EEG, electroencephalograph, puts electrodes on your head. And we don't. We're using something called fNIRS, functional near-infrared spectroscopy. In this case, it's not because it's better or worse, but just it's different. I have a collaborator at Tufts who's one of the pioneers in this field, so it's very nice to work with him. And it's a much newer area than EEG. So as a scientist, you'd like to dig somewhere where they haven't already been digging for 100 years. So that was our other reason for FNIRS. I'm not going to argue it's better or worse, it's just different. I'll explain how in just a moment. So what we're trying to do is for the disabled users, you tell them to do something special, like imagine moving your left toe, which they can't actually do, but you can pick up the signal of imagining moving your left toe in the motor cortex. You get a nice clean signal, and that can trigger the cursor to go up or the print button or whatever you need. So we're not doing that. We're going to have people do things, just do whatever they do naturally. Don't think about making your brain do something special. And then, of course, we'll respond in a way that the real world doesn't normally respond, because the real world doesn't normally respond to your thoughts. So that's the corner of the field we're in. So let me describe fNIRS. That's an example of the setup. Anyone familiar? Well, I guess, yeah, I know who's familiar with fNIRS. Yeah, this is a silly question. All my friends from Tufts are familiar. So fNIRS, you shine a light into your head. You thought your skull was opaque, but there is a range of light around near-infrared and infrared, a certain band of frequencies that go right through your skull. So which lets you shine it through the skull to the blood vessels below the skull, and the oxygenated and deoxygenated hemoglobin flowing around inside your head reflect or absorb different amounts of light. So what you shine the light in, you look for the light coming back out. As you can imagine, it's a very small amount of light, but it does come back out. And it's proportional to the amount of oxygenated or deoxygenated hemoglobin flowing around. We actually use two different colors of light. One picks up oxy, one picks up deoxy. So we're measuring blood supply to the brain. This can measure only about maybe 1.5 centimeters deep, not terribly deep. So there's a long history of studies showing that, yes, it's measuring brain activity, but it's only measuring it near the surface. It's measuring the same phenomenon that fMRI measures. You're probably familiar. Anyone ever have an fMRI? I don't want to put you on the spot, but so it's, you get in the tube and you hold very still, and this device measures the deoxygenated hemoglobin flowing around in your blood vessels. The difference is fMRI can measure everywhere in your head. This can only measure near the surface. On the other hand, it's way less trouble. I mean, this is a practical thing to do in a, you'll see in a moment, in a regular lab with, no fancy setup. And I'm also going to argue at the end that even though the equipment we use is kind of expensive, you could make a super cheap one of these someday. So I think it has a future, whereas fMRI is not going to be a super cheap one. So we're measuring something, a quantity similar to fMRI. It's sort of the opposite of EEG. So with fNIRS, you're measuring a very precise local area within a couple centimeters at most. So you stick the probe here, it's only getting input from here, not from anywhere else. With EEG, if any of you are familiar with EEG, it's very not localized. You put the probe here, and you're getting input from half of your head. It's just very spatially not localized. On the other hand, there has to be a bad news also. On the other hand, the temporal low specificity is much, much worse. So EEG gives you responses in milliseconds. Here we're getting responses in seconds. And that's not because of the equipment, that's because of the nature of the physiological phenomenon. When your brain calls for more oxygen, it takes a little while for the heart to send the oxygen. So the phenomenon we're measuring takes several seconds. The device fires away 10 times a second, but that's not the problem. Okay, so it's just different from EEG, sort of better for spatial, worse for temporal. It's possible to combine the two. We did one short experiment once, but it can be done. So that's what we're using. And I'll show you if I can make this go. Yeah, okay, the music is irrelevant, but in this case. But that's the device. It has little lasers over there, yes, and photomultiplier tubes there. A fiber optic cable carries the light in and back out. They end with a little rubber pad that goes on your forehead. Put that on. You put like a Nike headband around to hold it tightly against your head, and that's the whole setup. That's it. That's so if you've ever done an EEG experiment, there's no grease here. You don't have to wash your hair afterwards. Here's the fiber optic cable bundle. There's, I think, 18 of them because there's lights coming in and lights coming back. And in this experiment, we wondered just how much can you move around because that hadn't been done before. Can you actually use a computer? Can you move your head a little bit? And so we tried these different things to change your facial expression, use a mouse, use the keyboard to see if it would have an effect. And the answer was pretty much either no effect or an effect that can be calculated and canceled out. The only one that really messed us up, was scrunching, like frowning really tight, scrunching your forehead, because it pushes that rubber pad away from your head and lets room light leak in. And if room light leaks in, you're sunk, because that's so much more light than this little gadget. So we found that, yes, this works in reasonable kind of office or lab settings. Excuse me. We then did a feasibility study. This was starting about 10 years ago when it was not well established what these things were measuring and whether it's real and whether it's measuring systemic effects throughout your body or just measuring what's going on in your brain. So we tried this experiment. We're measuring, we in all of our experiments so far, we've measured here. You can measure anywhere on the surface of the head, not only about so deep, but it's much easier where you don't have hair. I know some people don't have hair all over their head, but it's much easier on the forehead. We had this plan where we were going to try and recruit subjects and say, this is unproven, but it's an experimental cure for baldness. Would you like to try? We didn't do that. The thing we're measuring, so now, anyone here a neuroscientist? All right, so now you have to shut your ears for a moment. No, that's okay. Roughly speaking, short-term memory, executive function, sort of cognitive workload kinds of things happen here. I think the people who raised their hands know a much more precise answer to that, but roughly speaking, this kind of cognitive workload stuff seems to be happening here. So our first experiment tested just simple short-term memory. The kind of thing, if I told you a phone number and I asked you to remember it, and you'd go, okay, 333-1212, you'd sort of keep saying it in your head. So in this experiment, at least this cube faced, you could only see one face at a time. There was a physical one that was on a turntable, and there was a computer one that was just a picture. And we asked people to tell us how many, say, blue, yellow, green, and red squares there were in the entire cube, but you could only see one face at a time. So you'd see this one, and you go, all right, 3 yellow, 1 blue. All right, 3 yellow, 1 blue. And it turns, okay, that was 3 yellow, now I'm up to 4 yellow, 2 blue, 2 green. So it's a short-term memory task. We tried this with 4 colors, 3 colors, and 2 colors, because that's more memory. And we were able, to classify the results. We took the measurements, and each bar here, the details don't matter terribly. Each color is a different subject, and these things are giving you classification accuracy in a 2-way classification. So chance is 50%. And you can see some subjects, the dark red one did quite well, the blue one not so good. Some subjects were better than others, but it's a usable percentage. We're nowhere near expecting 99% for something like this. But it's enough that you can build a system which, if it doesn't do too much harm when it guesses wrong and does something useful when it guesses right, would be a net win. So this gave us some confidence that something is going on in here. Yes. So we now have a sort of a hammer, and we're looking for a nail. We have, and I'm perfectly willing to admit that, we're not engineers trying to solve a problem, we're trying to improve human-computer interaction. So we have a way to measure this kind of workload-ish thing, and the question is, what could you do with that if you could measure it in real time? So, whoops, come on, that's our challenge. So the first thing we started doing is combing the fMRI literature. And you know they have those little pictures of the head with the different sections colored in. We looked for anything that was colored in over here. Anything that lights up on the forehead we're interested in. So we found, particularly this multitasking one I'll describe in a moment, we found some interesting signals in this part of the head. The other thing I should mention, maybe it's over there, no. All right, is we use a heavy dose of machine learning. Maybe I'll show you this picture instead. So here's an example of the data we get. There are actually 16 channels. 8 measure oxy, 8 measure deoxy, and there are 4, however many different locations that is. 4 locations here, 4 locations here. So 4 times 2 times 2. And these are just 4 of those different possibilities. This is 40 seconds worth of data, many trials averaged together. And the 3 colors are 3 different conditions that we're interested in. So our goal, we don't care which one does it, but our goal is for somewhere in the data to be able to distinguish the 3 cases. So you can see at the beginning of a trial, nothing's going on because we just gave you a task to do. Your brain isn't really doing anything yet. And it's too early to measure it. But after a few seconds, and even better after more seconds, these things tend to separate out. So just staring at that, you get a sense that, number one, it's not a beautiful, clean signal like, just nicely, cleanly separated. And number two, decent machine learning will be able to extract these things. So machine learning has been a big part of our work. We were actually inspired by a paper about 10 years ago by Desni Tan at Microsoft, who, I think he would admit, set out to show that with machine learning, any idiot can now do brain-computer interfaces. You don't have to be a neuroscientist. And so we took the bait. And I think he would admit that that was his goal. So machine learning makes a big difference in making it easy to do this stuff. And so the systems we build look kind of like this. You have a task to do, you have a regular old mouse and keyboard, and in addition, while you do the task, your brain generates some signal. And we measure it, we give both inputs to the computer, the actual mouse and keyboard, and whatever we measured, and that all drives the interface. So that's sort of the general plan. Okay, I'm going to describe first, not the first experiment we did, but the one that's the most straightforward to describe, and then I'll describe the first experiment. So in this one, a user on the ground is controlling drone airplanes, UAVs. And they're controlling several. Apparently, the Air Force believes that in the future, a single pilot will control a number of drone airplanes. Now I think it's 1-to-1, and sometimes even 2 pilots drive one, but apparently in the future. So this came from Missy Cummings' lab at MIT when she was here a few years ago. And we were glad to use something that we didn't make. So it's not a straw man. We didn't just make up something that works for our system, but we used something that was developed for a completely different purpose. So this is the control console for the UAV, their UAV system. And it's, the details don't really matter, but you have several UAVs to control. And it's a time-sharing task. So you send this one over here, and then you send this one over here, and then you got to check back with the first one to see if anything changed, because these places where you're not supposed to fly change from time to time. So he's going here perfectly happily, but oops, something came up, now you have to tell him to turn. So it's a time-sharing task. You got to keep going back and forth. So the question is, how many airplanes should you control? There's no set number. It depends on the situation. It depends on your own state. 2 airplanes heading for each other might be plenty to worry about, or 10 airplanes all going in a straight line might be easy. So we want to know how busy you are. And in this case, and all of our other systems, it's something you could perfectly well do if you had a knob and a third hand. You could say, now I'm busy, now I'm not busy, except it would be really annoying. So you could have a dial here, and you just turn it up. Every 3 seconds it says, are you busy, are you busy, are you busy? And we're trying to do this passively or implicitly. So we take the brain data, we run it through our software, we do some filtering, we do machine learning classification, and when the system says you're not very busy and you've been not very busy for a while, we don't want this thing to oscillate. If you stay at not very busy for a while, it gives you another airplane. The scenario is there's a team and one of your team members has given you an airplane. And then when you get too busy, we take away an airplane. So we're trying to sort of keep you in the zone, not too busy and not too bored. And so how do we know if this is working? We can't really tell whether you're truly busy or not. We don't have any way of cutting open your head and finding ground truth for this. That's true of all of our work. But what we can do is get end-to-end performance. We can say, with this system, which adjusts your workload to be, more correctly adjusted than without, do we get better performance? And the answer, of course, is yes, or I wouldn't have shown you the slide. And the answer always is never going to be super dramatic, because we're doing these subtle things. An airplane comes, an airplane goes. But I won't go through the details, but in errors was the biggest difference. People made fewer errors. So it's like playing a video game, and you can measure whether people make mistakes or not, and you can get an overall score. So with this thing, people had better performance. We claim, therefore, that the whole thing must have been working. It must have been correctly getting the data, correctly classifying the data, and correctly adding. But we can't go in here and look. That's just sort of a sad fact of these things. Okay, that was the most straightforward one. We also claim to be the only lab doing drone airplane research not funded by the military. This was just an NSF project. And we had a bunch of press about this project at one point, and I kept telling all my students, don't say drone, just say airplane. Because as soon as they hear drone, they're way off in an irrelevant direction. So we didn't have any actual drones. Okay, so with this experiment, this was Erin Solovey's research. The previous one was Dan Afrigan, these past PhD students. And we got this, she found a signal that detects when you are being interrupted. So you're multitasking, an interruption comes, and you got to switch. Is this interruption, are you in the middle of something that you're going to have to struggle to remember? So if you have a completely stupid task, like whack-a-mole, and I interrupt you, it's no problem. You go back, you whack the next mole. You don't have to remember any context. If you have a complicated task that has some memory associated with it, then when you switch, when you come back, it's going to cost you something. And we think it's going to cost you something in short-term memory. So this was a previously established result, and we built on that. So we gave people, so we built a similar kind of system, and I'll mention the steps here. One thing we have to do with the signal we get is take out respiration and heartbeat. Every time you breathe, you get some more oxygen. Every time your heart beats, the total amount of blood goes up. And then there's just jittery noise, because things are noisy. So we can filter those things out. They're at known frequencies. Then we do our training run. So we give people tasks of known difficulty and calibrate the machine learning model. And then we feed each trial through and get a classification. So this whole thing has to work in real time or we're not interested. Most conventional neuroscience experiments are not about getting things to work in real time. The problem with real time is not that you can't get a fast enough computer. The problem is I'd like to see more data. So you could get way better analyses if you could wait till the end of the experiment and then analyze the data. But we need a decision now. So that restricts what we can do. Okay, so in this particular scenario, you're driving two robots. A very similar idea. You had two robots, you're time sharing between them. This is one robot's view, and this is the other robot's view. Again, this was a task we didn't invent. My colleague Matthias Scheutz's group had come up with this, and they had established performance measures for it. There's a whole story that goes with this. The robot is supposed to go to a location that finds a higher signal strength and then give a transmission. And you, as the driver, you as the controller, operate both robots. When you get overloaded, too busy with this time sharing between robots, we switch one of the robots to autopilot. The assumption here, and pretty much every other system we build, is that autopilot is not as good as you with your hands on the wheel. Otherwise, you don't need this. Just put on autopilot and go home. So the assumption is it's better if you're driving, but if you're busy, it's better if the system drives. Okay, so that was the scenario. So one robot was always, you drive it all the time. The other robot was the autopilot was turned on or off, depending on the fNIRS data. And then Aaron had a very clever idea that what if this whole thing is just nonsense? What if we're just kidding ourselves? This is our first experiment. Let's just make sure. So I guess I should first say, so the obvious thing is this, the red robot looks to see if you have this branching signal, which is the signal for an interruption that actually changes your train of thought. And if so, we turn on autonomy. But she had the clever idea of, let's also try it backwards. Let's just plug it in wrong. Is that on the picture? No. Let's plug it in wrong. Let's try, when your workload goes up, we'll put autonomy off. When it goes down, we'll turn it on, just to see if the whole thing is just like noise and nonsense. And then we took other measures. We took performance, how well you did in this well-defined task. We did a NASA TLX. Who's familiar with NASA TLX? It's essentially, I thought everyone would be. It's essentially a standardized questionnaire that says, so, was that very hard? Or how busy are you? It's just standardized is the good thing. It's widely used. So it's a measure, a widely used measure of workload. So we did as much as we could here, and then we made this maladaptive condition that worked exactly wrong. Just to sort of give the system a kick and say, is there anything really going on here? And indeed, so in this chart, higher is better performance. So the adaptive system worked better than brain signal completely off, which was better than doing it wrong, doing it backwards. So this gave us some confidence that we didn't just make this stuff up. And just in case you're about to ask the next obvious question, these two conditions had each about the same proportion of automation and non-automation, just at the wrong time. So the difference wasn't because one of these just had no automation or something like that. So, yes. All right, here's, how are we doing on time? Okay, good, thank you. So this is a weaker signal we got, also from mining the fNIRS literature. And this is a preference signal, kind of like a Pepsi or Coke, a sort of an economic preference, which you can detect. You show people two things, or in this case, one thing, and you can infer their preference for it without them having to express it. So for this, we used IMDb pages, which are like a one-page, you all know what they are. It's a one-page description of a movie. And we'd show it to them, and then we'd try to guess from the brain signal whether they liked that movie based on its description or not. So, and then we wanted later to be able to predict that. So the same kind of idea, we took the data, we do the usual filtering, we build a classifier, and then there's a second piece of machine learning in this, which is the movie recommender. So we figure out from this system how well we think you like this movie or this web page. And then we feed that into a recommendation engine like Netflix, except we can get hold of it. Right. So we feed it into like mini Netflix, and it recommends another movie for you based on how you classified the previous movie. So if this is working, the movies you should be getting over time, movies that are more and more to your liking. The thing should be tailoring the movies to you. If it's not, they should all be equal preference. And indeed, the other thing we did, sorry, is we also asked people for their ratings. After we had guessed the rating, we asked them for it just as an extra check on what we're doing. So we took the rating that we inferred, and then we also asked them to tell us what their rating on a scale of 1 to 5 stars is. And actually, this result one is better. So the blue results are the control condition, and as you saw more and more movies up to 20, you like them about equally. The gray condition is the brain condition, so the movies got more and more to your liking, which is sort of what you hope for. And our favorite result is one of the participants said, "Can I write down some of those movies? I think I'd really like them." So again, it's a small signal, but it's asking nothing of the user. All of these implicit interfaces don't ask the user for any input. They take no trouble on the part of the user. It just happens, which is our goal. When do we quit? I'm trying to figure out how many of these things.
You can have like up to 45 minutes.
From now on?
Including questions.
Okay, fine. Okay, fine. All right, well, I'll show you this anyway. Anyone know what bubble cursor is? All right, how many people know Fitts law? That one, got it. Yes, all right, Fitts law. So bubble cursor is a way to beat Fitts law. It was sort of all the rage in HCI a couple years ago. Lots of papers about it. The idea is if you're here, so you can't actually beat Fitts law just with raw motion, but if you know what's on the screen, you can. So I'm here, I start moving the mouse this way. Do I really have to move it all the way there? It's the only thing there. If I'm going to click something, it's got to be that. So if you know what's on the screen, you can beat Fitts law by, as soon as you get close to something, jump right to it. But the question is, how aggressive should you be? If I go 1 pixel in this direction, should I jump right there and catch it? Maybe not, because it would make it very hard if you wanted to pick one of these other things. You have to go way around it to get to it. So how aggressive was the parameter? And when we see a free parameter that's too much trouble to set manually, we're in business. So we did that for this. We did a bubble cursor experiment where how aggressive the thing is, how far out it would capture the mouse varied depending on your workload. There's a little more to this. There were 2 concurrent tasks, and it's probably more detail than you want to hear. But once again, we got better final performance. Our measure, I won't do that. Our measure is always actual performance. So right, that's the one we do. So we got people to select things quicker. Okay. Then we started working on music. So here's an area, these previous experiments, all of the ones I showed you, there's a clear performance measure. Did the robot reach the target? Did the drone airplane not crash into the mountain? There's clear measures. We then went into music. This is my student Besta Yüksel, who dragged me into something a little more creative. And we were interested in music interfaces. So we looked here for something, again, where there's something you wish you could control with your brain or with a third hand. Is anyone familiar with the kind of cheesy keyboard that automatically plays an accompaniment? All right, yes, you press down C, and it goes junk, 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 all automatically. And you press another note, and it transposes that. So we made a simplified version of that you play something very simple, and it adds some extra notes for harmony. Very, very primitive. But the question is, when would you like to have the harmony, and when would you like us to leave you alone? And then the difficult part is, how do we evaluate it? Because we don't know whether the robot reached the target. So this was one where we don't have a nice, clean evaluation. I mean, there isn't a way. We asked people for their subjective views. Just evaluating how good the music they played doesn't work at all, because you have to normalize for how good a pianist they are. Some people just will play better than others, irrespective of our system. So that didn't work. We also found we couldn't really work with serious musicians. They hate this. Serious musicians, we had some music majors working on this, they've spent 20 years learning to play the official, normal, standard piano. Leave it the heck alone, thank you very much. I don't want your new piano. So, so someone who's devoted their life to playing a regular piano doesn't want this stuff. But a much larger population of people who just kind of hack away at the piano might. So that was the idea. You play something very simple. In this case, you play these notes that are colored in blue. We gave you super simple things to play. Our target audience was people with a couple of years of piano lessons in their past and don't really play, but they could read enough music. So you play a couple notes, and sometimes we add some extra harmony and sometimes we don't. When do we add the extra harmony and not? You guessed it. We're going to measure your brain signal and decide when to turn this thing on or off. So let me show you what this looks like. Yes. Oh, can we get more volume?
Brahms is a novel brain-computer
Thank you.
interface integrated with a musical instrument. It adapts passively to users' cognitive state during musical improvisation. The system adds or removes musical harmonies based on users' cognitive state as measured with fNIRS, a brain-sensing technology. Our research showed that users preferred this novel musical instrument over other conditions because they felt more creative. Here, the user plays a single note with their right hand, with no adaptation by the system. Here, the system adds a note 1 octave above the user's note, slightly enriching the sound. Here, the user plays a single note with their left hand with no adaptation by the system. For the left-hand adaptation, the system adds the octave below as well as the third of the chord. This adds some harmonic depth and richness to the musical input provided by the user. The user can also play both hands at the same time, and the system will adapt to each hand independently. You can hear the musical richness added by the system even though the user only plays one note with each hand. Here, a user creates an unscripted musical improvisation using a simple 1-4-5-1 chord progression as a starting point.
He's actually a ringer. He's a music major. Very good musician. So you can see there's 16 places where the lasers shine into fiber optic cables, and 2 coming back. So based on his brain simulated in the video, the extra notes are seen. So you get the idea. So before we did this, we had to do an experiment to see, can you play the piano and not screw up fNIRS? Nobody had studied that before. And we did that, and we gave people a very easy piece to play and a harder piece to play, and measured their workload, and got very clean results. So now it's turned back off. So we found we could classify a hard or easy while they played the piano, and whatever motion, we didn't tell people to hold still or not, but you know, whatever motion we got didn't mess us up. I'm sorry, what? Oh, same old thing. It's a prefrontal cortex workload. Oh, which way? Is that the question? We didn't know, and we tried both. Yes, that's a very good question. So, when I'm busy, does the thing kick in, or when I'm not busy? Our hypothesis was when you're busy, we should leave you alone, and when you're doing fine, we'll kick in. We tried both. They both seem to work better than no adaptation. The first one worked somewhat better. But this is all questionnaire data. This is, you ask people, did you feel expressive? I mean, did you feel that this thing helped you express yourself better? There's no other evaluation here. There were nice, clean results of subjective measures. So that's what happens when you do music. You don't have nice, clean measures. But here's another thing we did in music. Also, Besta did this. So here we tried to work on learning. So the idea here is you're trying to learn a piece of music. And how many of you took piano lessons ever once? All right. So you all know they give you a new piece to play, and first you learn the right hand, let's say. And then when you can play the right hand correctly, they say, okay, now start playing the left hand. So the question is, when should we switch over? And in this case, we actually had a 4-part Bach chorale, so you learn one line, and then the next, and then the next, and the next. So when should you add the next line? And we said, not just when you can play it perfectly, but when you can play it well without struggling too hard. If you can just barely play it well, maybe you're not ready. I mean, probably a good piano teacher can kind of intuit that, but we're trying to make a machine. So when you played it correctly, it's a MIDI piano, so we can analyze the notes, we know what's being played. When you play it correctly with low mental effort, you get the next lesson. So
Learn piano with Bach, an adaptive learning interface that increases task difficulty based on brain sensing. Bach, or Brain Automated Chorales, is an adaptive musical learning system based on brain sensing that helps piano players learn Bach chorales. Bach uses functional near-infrared spectroscopy, or fNIRS, which has been demonstrated by HCI researchers to measure user cognitive workload.
same setup, different person.
In this paper, participants were presented with varying difficulty levels of a Bach chorale. Using Bach, we measure the cognitive workload of participants to determine when they could cognitively handle a higher difficulty level. Bach increased the difficulty level of the musical pieces as learners' cognitive workload fell below a certain threshold,
So
indicating
we
that the learner
simplified
could
the Bach
handle
chorale a
more
little bit.
information. Each level added a full line of music. Participants were given 15 minutes to learn a piece with Bach and 15 minutes to learn a piece the way they normally would in a control condition. They played the pieces once all the way through at the end of the practice session. This final performance was recorded and analyzed for accuracy and speed. Performance data showed that participants played with increased speed and accuracy when they
Each
learned
line
with
is
Bach.
one person.
Furthermore, participants said that they felt that they played better and learned more easily with Bach. Bach demonstrates that a real-time adaptive brain-computer interface can improve learning in pianists by monitoring and adapting to cognitive workload.
So I'm not being an expert in learning science. I'm loath to claim that this would work in many other kinds of learning, but when I've talked to colleagues, they seem to think, why wouldn't it? So here we got some objective data. They learned the piece in less time. So that's a little bit more objective. All right. Another experiment we did was with Google Glass. Anyone remember Google Glass? Which apparently is coming back. It's coming back for people in factories, not for people in bars. So that seems to be a better use case. So anyway, but what we suggested is Google Glass, if you remember the thing, has a fabulous way it can give you output. It connects to the internet. It can give you all kinds of information that Google has access to. It just doesn't have a way to tell it when to shut up. It has kind of awkward input. It has very nice output, but it has this thing you stroke on the side of the glasses. It's kind of a pain. So wouldn't it be nice if there were a way to tell this thing when to give you information and when not to, and whenever you need a third hand, we're there. So what we did here was we had an experiment. This is sort of internal details, but we had an experiment where you're using Google Glass to pretend to ride a bicycle through a 3D environment, and you're delivering campaign literature. And there's extra information that Google Glass can provide you that gives you better targeting of the campaign literature. But if you're busy, we'll leave you alone and you just go by what's on the mailbox. So you either deliver the literature based on what's on the mailbox, or you also check Google Glass and do this more targeted thing. The other argument we had was fNIRS device could probably be built into Google Glass someday. It's just not that hard. We didn't do that. So here, but it's feasible.
Wearables such as Google Glass have the capability to deliver a rich store of information to its users with an immediacy that surpasses
for
the
this,
current
Vesta was the
generation
narrator. It wasn't
input-output
actually her
devices.
project. But she's our
However,
best narrator.
delivering information at the wrong moment or delivering too much information can disrupt the user's current situation and harm performance. To measure cognitive state, we use fNIRS, a non-invasive brain sensing
By now you've
technique that
seen
measures blood flow in the
That's-
prefrontal
that's the
cortex
side that goes against the
engages
head.
cognitive states, particularly high and low workload. The filter system receives streaming information estimating the user's cognitive state, shown in the left pane. Possible notifications to send to the user are shown in the middle pane. Upon receiving a notification, Filter consults a moving average of user state predictions, deciding whether or not the user is fit to handle more information. We tested our system in a real-world simulation. Our results showed that when we give users
So that's
notifications
what's in
at
the
the right
glass.
time,
And
their
that's what's on the
performance in
big
the
screen.
primary task does not decrease, allowing them to complete a
are the
substantial amount of
birth
additional
dates of
work
the
in the
voters.
secondary task.
Right, so when they can handle it, and they got the extra information, and once again, they performed better when the extra information was turned on and off appropriately. Okay, maybe we'll talk about it. So directions we've gone lately and are going, one is we haven't done yet, but would like to broaden this. Implicit interfaces don't have to be all brain, but that's what we've been focusing on. But there are other things you could measure, like, as I mentioned, skin resistance or heart rate variability is another one. So that's a wrist device that can measure some of those properties. So we've been talking about including those measurements, but we still sort of focus on fNIRS because that's an area where very few other people are working on, and so you never want to be the only one working on something in research because then people will ignore you, but you don't want to be one of 1,000 either, so we're trying to find a happy medium. We worked a little bit trying to make a two-way brain-computer interface. So the idea is we're measuring brain information. Could we also put something into your brain? Anyone familiar with TDCS, transcranial direct? Yes, current stimulation. This is not the old-fashioned your giant electric shock that wipes out half your brain thing, which is given to people with severe problems. This is a small DC current that is run through your head. And seems to kind of activate one part of the brain at the expense of another. It's like it alters the balance of what parts of your brain, this is very roughly said, alters the balance of what parts of your brain are more active or less active. So it makes some kind of a change. And what we wanted to do, this has been used for post-traumatic stress syndrome in cases where they want to give you some of this electricity for a while and then send you home and you're going to be better for the rest of the day or the week. We wanted the opposite. We wanted to do this in a dynamic situation where we measure your workload and we decide right now you need a little zap, and then now you don't need it. We wanted to just give a very tightly time-controlled signal. The idea was, remember those UAVs? Imagine the workload goes up and there is no team member to give the extra airplane to. So in that case, we give you a little zap. We need better performance from you just for a short while, and then we let you go back down. There's no point in just zapping people all day. It's like, a bad boss. That's not going to work. But a little zap and then a rest period, perhaps. The problem is we couldn't get a short-term effect. It may still be possible. We didn't push this very hard. This is my student Sam Hinks with the TDCS gear. It took 9 minutes for us to get a response. Which, again, if you're coming in for your weekly PTSD treatment, is no problem. And we don't know how long it took for it to fade away because people didn't sit there that long. So 9 minutes is too long, we thought, for something happens and we're going to respond. So we played with this. For the moment, it's on the back burner, but I don't see why there won't be some kind of two-way brain-computer interface in the future. We're just finishing up. Anyone writing a paper for the CHI deadline next week? We're just finished writing up a paper on interruptions where we want to change the nature of the interruption. Most interruption studies postpone or mute interruptions, but we thought, let's do something else. Let's change the nature of the interruption based on how busy you are. If you're busy, we'll give you a very small interruption that you can ignore. If you're not busy, we'll blast you with the interruption so that you can respond faster. because you didn't have anything else to do anyway. So we're tinkering with that, and we have modest results there. We're also working on languages for building these kinds of things. So I've described all these cool interfaces to you. We've built every single one of them, but my poor graduate students just hacked them out of whatever kind of tools we had, standard tools. Years ago, some of you remember the early days of the graphical user interface, when they were also hacked out of whatever was available. You put individual bits on the screen when you wanted a menu, and then toolkits came along. Nobody does the individual bits anymore. Now when you want a menu, you call menu out of the toolkit and it's all done for you. So we're wondering what would be the right languages and abstractions for this kind of interface. The idea here is you could just write everything as read input device respond, but I think there's two dialogues going on. There's the normal dialogue of click and do whatever you do, and there's this dialogue kind of superimposed on top of it, which is as your brain state changes, we kind of make this global change. So I would like to be able to program that by having two different specifications, not just one giant thing that says read mouse, read fNIRS, read this, read that. So my grad student Tomoki Shibata is working on developing languages for doing this. All right, so that's stuff we're up to. I don't think we need all of these. Another one we're thinking about. Haven't done this. Somebody do information visualization? Somebody must be doing InfoVis, or you're familiar with in InfoVis. A big issue is focus versus context. Should you give the screen space over to the main data, or should you give extra context information of some kind that helps you know where you are? And you almost always can't do both. It won't fit on the screen. So this is another thing where you could control this with a knob, but how about we do it automatically? When we notice some change in your brain state, we'll gradually fade from one to the other. So that's one that's been kicking around, but we haven't actually built it. I won't show you that. And then we're trying to come up with a way to look at these different passive interfaces or implicit interfaces. This is not final, and I welcome your comments or changes, but we divided the world up on two axes. One is, does the adaptation that responds to your brain happen immediately or later? So in the airplane thing, as soon as your brain state changes, an airplane gets added or taken away. In the recommendation system, your brain state affects a future recommendation, so it's not triggering something. So that's one way to look at these. Is it an immediate effect or a delayed effect? And the other is, where is the change happening? Is the change happening to what we call the syntactic part of the user interface, the front end, or the back end? So in this focus versus context, the task isn't changing, only the interface to it is changing. In this one with the robots, one of the robots is actually going on autopilot. You have less work to do. The task is actually changing. So that's how we've divided up this field. But I don't know if everything will fit into this neatly. We'll see. Okay, and one more thing to tell you. This is my argument for someday there will be cheap fNIRS devices. This is my colleague Valencia Kumsen at Tufts has developed this thing is like, so big. A small board. This doesn't work well yet, but you get the rough idea. This thing goes on your forehead. There's light sources and light detectors. They're just right on the printed circuit boards. The whole thing slaps against your forehead. It gives very noisy results at the moment, but if this were to be produced, it would cost almost nothing. These are super cheap components, and they're working on refining it, and they'll get better. So it's not workable at the moment, but there is a future for fNIRS. I'm not describing something that only the military can afford. There'll be. Okay, I think that's enough of this. Let's just say thanks. Okay, this is my group as of actually a couple years ago, I have to say. Some of these folks are still here. Some of them are now professors and other kinds of grown-ups. Okay, questions, comments?
So I've got a mic if anyone has questions.
Hi, how are you?
Hi, good. Nice series of experiments. Can you say something about the classification? Because usually with machine learning and classification, you need fairly large data sets.
Yes. So we are fighting with the nature of machine learning. You'd like large data sets, and we can't get very large data sets because people won't sit still for this for all that long. And we like, 10, 20-second trials. We'd like not like a quarter of a second trials. So we're getting okay results, but we are just like doing everything wrong for machine learning in the sense that we don't have a lot of trials. And we also, the trials form a time series, which machine learning tends to not like. So we are getting usable results, but we're feeling like we're at the wrong end of machine learning. And we're just starting to work now on combining the inputs over many users. We always in the past have done individual calibrations, but we're getting some better results now with many users because then you have more data, even though, of course, it's across different users. So you're absolutely right. We are pushing our luck with machine learning. Excuse me. On the other hand, when we started this work, our colleagues Sergio Fantini and Angelo Cesaroli in biomedical engineering who were working with us, and they were our fNIRS experts. And we said, well, what's going on here? And they said, well, bring us the printout. Okay, there's the chart right there. There's the workload went up. I said, that's nice, but are you going to sit here all day while we run our experiments? That was sort of the state of the art, was somebody looks at it. So we managed to get better results than they were accustomed to with machine learning, even though I'd say we're handicapping ourselves. You're quite right, yeah. Yes?
How do the results of your interface compare with the results that one gets from a lie detector, for example?
I don't know. Lie detector is essentially the same kind of passive physiological device. But it's not measuring, is it measuring workload? It's measuring a sort of arousal. I don't know is a short answer. And I don't think people have built this kind of adaptive system using skin resistance, which is what lie detector uses. Yeah.
Thank you. I'm curious if you've observed any sort of like Schrodinger effect. Do you find that by observing the workload of somebody and changing some sort of part of an interface, that they then respond to that, which change their responds their mental effort?
Yeah, good point. The first question, which you didn't ask, but I'll answer anyway, is should we have an indicator light saying when we think they're in high workload or low workload? There's an argument I've had with every one of my students, and I always say no. I don't want you to think about this. We're not kidding you. Of course, you got a brain sensor on, but just don't think about it. We don't want it to become, like you say, sort of a biofeedback loop. Ooh, look, I made it go up. So we're trying to avoid that. They're not usually there for all that long. It's about, in an hour-long session, maybe 20 minutes is calibration and 30 or 40 is experiment. And these trials are fairly long. So there's probably not enough time for them to really get in sync with that. But the short answer is I don't really know. We had the same thing back when I was doing eye tracking interfaces. Should we put an indicator up showing where the eye is pointing? Well, my feeling is you know where your eye is pointing. You don't need it. You need it for demos if other people are watching. And then there's another funny phenomenon. Anyone done eye tracking? You know this phenomenon. If you put a cursor up where the eye is looking, there's usually a small error. These things aren't perfect. So you're looking there, the cursor is there, and it's jiggling a little bit. So you look at it because it's interesting. And now that pushes the cursor, they just watch the thing go off the screen, and you don't know why, but it happens all the time. So we're trying not to make a biofeedback system. So we're not trying to kid people, but we're trying to just say, don't think about it, don't worry about it. And so far in our limited size experiments, that seems to be the case. We had, in the robot, one robot was red, one robot was blue, and we didn't explain things very thoroughly to the users because we didn't want to. And at the end, one of the subjects said, the red robot was more helpful. Which is just, it's just what you want. Like, don't worry about the details. We're just going to make your life better. That's my goal. Yeah. Or you have someone else queued.
Thank you very much for everything. I was very interested in your Brahms and musical experiments. And the second one where that people seem to learn the piece better based on reading. And I was wondering if you thought about applying that to other domains. For instance, having young children learning math in school. And I was wondering if you all thought about using something and detecting when kids were struggling with math problems, and if you could think about things that could help them.
Is there anyone here from BrainCo? BrainCo is a brain interface startup here in Cambridge or Boston, or nobody wants. So they seem to be doing something like that, and I bet other people are too. I don't know exactly what they're doing. They're a small startup. I don't know what I'm supposed to talk about, and I don't even really know what they're doing. But so it's like, but at least they seem to be interested in doing that. And there are other people too, I think. Yes, I bet it would make a lot of sense. To do a class, you'd have to get a bunch of these, which will someday be possible, but right now is expensive. Yeah, I bet you could do that. When we started this, I was really reticent about claiming other kinds of learning, but more and more people seem to be telling me that, yeah, it'll probably work fine.
We have another question?
Yeah.
Two quick questions. One, have you tried it on the musical piece on a very young children and see if they can learn the music better because it creates new pathways?
No. And not only no, we stay away from people, from young people, old people, left-handed people. The brain is so different from person to person that to do reasonable experiments early on, you have to choose a very narrow population. So no, we don't go anywhere near young people or old people.
Was the device ever calibrated against fMRI?
Yes. Yes. So what we have done, you saw they have fiber optic cable, so there's no actual metal. Yes, my colleague Sergio has put people in an fMRI, ran these things to their head, and you get the same data. Yes. Yeah. Yeah.
Cool. Any other questions? So, okay. And then I have one too.
So then first of all, thank you very much. Very interesting. You mentioned the constraint of it being much easier to sense areas without hair. And I'm wondering sort of what trade-offs could there be, like, the signal that you chose to focus on for these experiments? Could there be other related brain functions that are sort of working with that like if you were measuring them simultaneously would affect the way
question.
the interface should respond?
Yes, we actually started an investigation along those lines. So anyone familiar with default mode network? It's all the rage in psychology. He's familiar with it. So default mode network is the idea that when your brain isn't doing anything, it's still doing stuff. It's not just turned off. And maybe when we're measuring workload, what if when you're not doing a useful task, you still have high workload, but it's the default mode network kicking in. So we'd like to distinguish those two things. And for that, we began exploring something going on over here, which is negatively correlated with what we're measuring on the front of the forehead. So when we see a negative correlation between there, we do have a new probe that gets in the hair. Over there and here, we think we may be seeing default mode network. So yes, we just started tinkering with that. There are fNIRS devices that cover your whole head. It's possible to do it, not inside, it won't go deep, but it'll cover the surface of the entire head. They're very expensive, like $500,000, and they're very uncomfortable. One of my former PhD students, Leanne Hirschfield, has one in her lab, and it's got these sort of spring-loaded pokers. They don't break the skin, but they just poke against you, and you have to get them. So the deal is you have to get each one to go in between the hairs and touch the scalp, because with this small amount of light, a hair would just block everything. So all it has to do is get between each hair. So it is possible, and people have done whole head fNIRS data. But there's a lot going on here, and that's kept us busy so far.
How important is precise forehead placement? I mean, does it matter if the devices slide even a couple centimeters one way or the other?
Yeah, so when we, so until recently, we always just stick the thing on your head and then calibrate you in that setup and don't let you take it off till the experiment's over. And it doesn't slide. It's a fairly tight headband. So in our experiments, the calibration is done with exactly the same placement. We did one experiment once with not very clean results where we had people come back the next day. And so the answer is we don't really know. The current probe we're using, you saw that one with the 4 in a row, the current probe we're using has 3 in a kind of a circle. And I think that's going to give us more tolerance in that if this one isn't getting it, then this one will get it, that we'll have it placed in a way that one of the probes will get the right spot. So the answer really is we don't really know.
Hi there.
Yeah.
Are you missing out any functions because the fNIR device goes only few centimeters deep, you said, right?
Oh, sure. We're missing, yes, the whole rest of the brain we're missing. But we don't want to stick you. Sorry, what?
Which functions you're missing out, which you should use? You had that.
Everything else that goes on, emotion. I don't know. I don't know. Someone who's a neuroscientist can say what happens that's not 1.5 centimeters down. Everything else inside of your brain. You can get the whole head, the surface of the whole head, but you just can't get all the rest of the functions of the brain. So we got to look at it a different way, I think. We got to look at this as sort of a glass is half full. This is amazing that you can get this information at all. And so let's do what we can with it, rather than complain that, yeah, I'd also like to get this. So I'm thinking of, it's more information than you had before. What could we do with it? Preferably that isn't too harmful. So we want to do things that won't annoy you if we guess wrong, because we are going to guess wrong, and would be a serious win if we guess right. So that's the philosophy, rather than I want a complete measurement of the brain. I don't know. It may be unsatisfying, though. Yeah.
This was really interesting. A question that I have is, have you looked at combining voice interfaces as well as visual interfaces in the feedback loop?
We had an audio NBAC in one of these experiments. So the NBAC, I didn't mention, the task we used for memory in some of them was delivered by voice. But you didn't, I forget if you responded by voice or not. A little bit. And not expecting or seeing anything different. But we weren't really deep into voice interfaces. Yeah.
Any other questions at the moment? All right, then you can never ask another question again. I'd like to thank you so much.
Thank you. This is a pleasure. And thank you all for coming.